Welcome to Statistical Modeling. In this video, we'll discuss how we can write down likelihood contributions in the presence of censoring with survival data. So how do we handle survival data in a likelihood context? Well, essentially all we need to know or to characterize is the survival function. So you may have seen distribution function, which is the probability of some random variable being less than or equal to a specific value. The survival function is 1 minus this distribution function, and it fully characterizes the distribution, the law of the random variable t, which is here our time to event. So if we know s, right, we can you ask me, okay, well, what's the expected survival time, or what's the time at which half of the people are dead? If you know this curve, you have all the information that really is needed. Often we will be more interested in survival analysis in describing periods characterized by higher failure risk, and this is encoded in the so-called hazard function. Okay, so what is a hazard function? It's the probability of dying. So given you survive until time t, what's the probability of basically failing just then in a very short interval? So we view this as the limit when you're in a very short time interval after time t. And so basically it's the density divided by the survival functions, the probability of failing at quote t, given you've survived until then. Okay, so divided by probability of your failure time being bigger than t. Okay, and this is so-called hazard. It's in a way it's the instantaneous probability of dying at a given time. So the higher the hazard, the more likely you are to fail at a particular time. So here are two examples. The survivor function goes from 1 at time 0, everyone survives, and then it drops down towards 0. It may not be seen in the data, but this curve goes from 1 to 0, and it decreases monotonically. The hazard function is the density divided by the survival function. So here you can see the hazard is increasing. The hazard is pretty steep, very close to 0. So there's higher initial risk, and the higher the hazard, the steeper the survivor curve on the left will be. We also have here a bathtub shape hazard. So this is very common in reliability data and also human survival or generally animals. There's a high mortality initially, so risk rate is very high, and then it drops. So for example, you could think of miscarriage, childbirth, diseases at early age when the immune system is not so great. Or if you're thinking about manufactured goods, there's defects, initial failures, and then if it hasn't failed early on, then it's unlikely to fail, and then the risk is low for some time, so the hazard is low and sort of constant, and then it gradually goes up as time goes on, right? So if you think about people, this curve would be a bit stretched, but you would have a very long streak from maybe age 5 or so until age 60 where people are not so likely to die, and then it goes steeply up and increasing. So what do we know? In the previous video we've looked at censoring, so recall right censoring. We only know the event happened beyond time 0, right? The person, we for example stopped the study, the person was still alive, we hadn't experienced the event. So all we know in terms of contribution is that this time exceeded little c. Okay, so survival time exceeds c. So if you have censoring, rather than just having a column in your database for the response time t, you'll have a dummy variable delta, that's going to indicate you what this time represents. And typically if delta is 1, okay, that means you've observed the failure time. So the person, for example, died, or the unemployed person found a job. So the time you see is the true time. Or it's an indicator of right censoring. Okay, delta naught. That means the time must exceed this value. I don't know precisely, but it's at least that. Okay, so just be aware, the time you see might be a lower bound than the actual time. So in terms of likelihood contribution, well, the people who've observed time might have the density contribution, right? Know what's the instantaneous probability of dying at that particular time. And for the others, I know, well, okay, the contribution is, it must be at least that. And so these two events carry different information about survival time. So I can break down my likelihood basically in the contribution. The log likelihood is the sum for independent observations of the contribution of the people who failed that I've observed, and the contribution of the people who are right censored here, okay, for which I have the observation. And right censoring is much less informative than the actual observed failure time. So let me show you an example with a parametric model. So here I have not specified the distribution, but I could just pick any distribution function of a positive random variable. Okay, so there's many ways you could approach this problem. Either you pick a family of distribution, that's the so-called parametric models, for Weibull, log normal, Gompertz, Mayhem, exponential, that are very common for survival analysis. So the benefit is that they can readily be used to incorporate potentially explanatory variables, but we'll see other avenues. If you specify a distribution function, it's continuous, so it somehow extrapolates beyond the range of the data, and it smooths out where you have not necessarily seen data. But it's not necessarily flexible, right? If you're specifying, you're forcing the survival function to have a particular shape, and for example, your distribution function does not include does not capture bimodality, you'll get a poor fit, and so you're subject to misspecification. So it's very popular among practitioners to go the non-parametric route, and we'll explore examples of non-parametric estimators later. But here you don't specify a distribution, rather you just consider this as a sort of optimization problem and find the best fitting model. Drawbacks is that it's going to actually yield probability only at observed failure time, so it yields discontinuous estimates of the survival function. Rather than look like a smooth curve, it's going to look like a step function. The curve, if you've observed a failure at the highest time, there's probability 0 of seeing something beyond that. Okay, so you cannot really extrapolate. If you have a lot of observation, very large sample size, basically that's the best thing you can get with the least requirement. It's highly flexible, but to a certain extent. So here's a parametric example. I will not go this route, but know that it exists, and there's various extensions. So just to show you the effect and how we could just model or handle these time to event data. So I'm going to assume that my failure times are exponential, so they're independent and they all have the same distribution, exponential, and the exponential here is parameters in terms of rate. Okay, so the expectation is 1 over lambda here. So the survival function I can write down, that's exponential of minus lambda t. And if I write down the hazard, okay, it's little f of t, the density divided by the survival function. Turns out that the hazard is lambda and it's constant. Okay, so the risk of dying at any point in time is the same regardless of the age, in a way. Okay, so this is sort of memoryless. So time to event, which could be modeled with exponential variable, the time before you catch the next boss. Okay, so the log likelihood I can write as the contribution from the censored observation versus the non-censored. Okay, so if you take the log for ST and the contribution from the density, you basically get this expression, and if you differentiate this with respect to lambda, and you solve the gradient equal to 0, you'll find that the maximum likelihood estimator is a sort of reciprocal mean, but the weight is, so you have all the times that are recorded, except that the weight is the sum of observed failure time, not the total sample size. Okay. In particular, if you've observed no one failing, you'll estimate that survival is infinite. That's seldom, that doesn't happen. But perhaps more interesting is the fact if you're looking, for example, at the uncertainty of your mean, weighted mean estimator. So we obtain the standard error is the usual way from the observed information matrix. Okay, so you compute this weighted estimator, and you get here the observed, so the negative, the Hessian, and you'll see that actually censored observations do not contribute any information about observed failure time. Okay, so that's a particular aspect. Bear in mind that censoring contributes less information than precisely observed time, and that will have impact on inference, because that means that if you have a lot of observations but most of them are censored, there's limited information available about events. So this completes the video. Thank you for watching.